So the next force we're going to talk about is air resistance. Now, air resistance is one of those things that if you wanted to get a degree in physics and would like to explore something interesting, you could explore air resistance. I mean, it's still up in the air. It's all chaotic dynamics. It's all particles being moved by another object. It's very difficult science. So when we talk about air resistance, there's actually two equations that I've seen for air resistance. The first one I've seen in aviation. We talked about aviation and we talk about objects going through a wing going through air. We tend to use this equation in that the air resistance is equal to 1/2 a drag coefficient, which depends on the geometry of the object. Things like flat sails may have a drag coefficient of something like 2.5. An aerodynamic airfoil may have something like 0.05. Okay, so it's just a number based on the geometry of the object. This next term is a rho, and it's referring to density. Whenever you see a rho in an equation, it's referring to the density of an object. So this is actually referring to the density in which the object is traveling through. Whether it's air, which has a density of 1 kilogram per cubic meter, or water, which has a considerably higher density. That value, rho, is just the density of the medium in which it travels through. A is equal to the cross-sectional area that's traveling through it. By moving in this direction, I'm talking about how much cross-sectional area I'm experiencing. Larger objects are going to experience larger force. It only makes sense. You're only pushing through more air if you have a larger object. The last one, and let's make this a little more obvious, is velocity. How fast an object's moving. Velocity squared doesn't give me a direction. I get rid of the direction once I square it. So it's kind of talking about speed in this case. That is one equation for air resistance. In some cases, there's a simplified version that says that the force of air resistance, is proportional to some constant, whatever that constant may be. And I'm sure this constant is taking into account all this other stuff, times the velocity, which means that the force of air resistance is directly proportional, or should get rid of that proportionality and say that it's equal to. Okay, tomato. I guess it's not that you can just throw this out, but I've seen it in both cases. I've seen it in text in both cases, that it's v squared or v. There's no definitive equation. There's no specific that this one's correct and this one's wrong. We should never use this one again. There's nothing out there like that. There's just taking an object and shoving it through air is mathematically very complicated, because you have to talk about every particle that's colliding with that surface. So, is it this one or is it this one? I can't tell you. I can't give you a correct answer. The thing that you really need to know about terminal velocity is that this force of the air resistance grows with velocity. As faster and faster an object goes, the more force it experiences. So as an object is falling, it's heading down and it's going faster and faster and faster. Well, as it's moving down, we know that the air resistance will start to increase. So as the velocity grows, so does the air resistance. Okay, so here's your velocity, here's your air resistance. So as the velocity grows, so does your air resistance, to the point where this value of air resistance, whatever it is, ends up equaling the weight of an object. When you experience that, when this air resistance is equal to the weight of the object, that means that object is no longer getting any faster. The acceleration at that point is equal to 0. So at this point, when the acceleration is equal to 0, we experience what's called terminal velocity, which means that the object will just fall at a constant velocity. Now that constant velocity, if it's you jumping out of a plane in air, is pretty high. You're still going to hit the earth going really, really fast. But if it's a marble dropped in some high viscosity oil, It may not be as high. It certainly won't be as high. I mean, it depends. I mean, in that case, it's not necessarily air resistance. I'd say it's more fluid resistance. But the important point that you get out of here is not these equations, because neither one of these could be correct, one of these could be wrong. But nobody's been able to agree which one's correct and which one's wrong. The important thing is that there's this property called terminal velocity, in which that this force of air resistance grows and grows and grows and grows and grows. So every second that an object falls, the acceleration of that object per second keeps getting smaller and smaller and smaller and smaller and smaller until it reaches terminal velocity. And at that point, the object no longer experiences an acceleration, and the force of the air resistance is actually equal to the weight of that object. Okay? That is air resistance.